Hello Year 10. As always, let's start with a starter quiz. The answers will be on the next slide. If you are watching this on YouTube, of course, you will want to pause the video now so that you don't see the answers. Okay, have a go. Let's see how we get on. Okay, so marking everything that you've done. Important questions here in relation to today's lesson. Make sure you are happy with questions 1, 2 and 4. Okay, if you've struggled with those, it might be worth having a quick look back over some of your older notes to make sure that you are confident with the terminology and the equations from before. So today's lesson is the second part of the core practical. We're going to use the equations again, we're going to look at how we measure it, and then as per usual we will explain the issues we faced and how we improve them.
Welcome to part 2. So this is the second core practical, the second part of that core practical, where we're looking at the speed of sound in a solid. Now straight off the bat, if we think about the distance divided by time equation, it's going to be pretty much impossible. Granted, I could hit the rod on this end, and I could try and measure how long it takes to get to that end, but the distance, granted, is easy to measure. The time is pretty much impossible. First of all, I can't even see the wave, so how am I meant to get it there? And second of all, the speed of sound in a solid is incredibly quickly, right? In metals like this, we're talking close to 5,000 meters per second, so 5 kilometers a second. The distance from here to here is probably 60 centimeters. The likelihood of me being able to accurately measure the time it takes to get from here to here, not going to happen. So we've got to have a different approach.
Right, so as we said, the aim of this practical is to measure the speed of the waves in the metal rod. Now, as I just said, you can't use the distance divided by time equation because it's too quick and you can't see it. So we need to use the other equation, which is wave speed equals frequency times wavelength. So we've got to find a way to measure the frequency and we've got to find a way to measure the wavelength. So let's have a go.
My only real option for measuring the speed of the sound in this metal rod is using this equation. We can't use distance divided by time, as we've said. This is our only option to measure the frequency of the sound in the rod and to measure the wavelength. Now granted, if we tried to do this visually again, it would be impossible. But we have a few tricks that will allow us to do this a little easier. So the first thing, handy little trick, is that the wavelength of our sound in the rod is actually equal to twice the length of our rod. So it's a handy little trick to help us do this. So all I've got to do is take my trusty wooden ruler that every science teacher has somewhere and measure the length of this rod. Now if I measure the length of this rod, while it's moving it's a little difficult, it is 61 centimeters. So I know my rod is 61 centimeters long. The wavelength is always twice that, so we've got 122 centimeters. But as we talked about earlier, can't have centimeters, my SI units of meters, so I need it in meters, which will be 1.22 meters. So my wavelength is nice and easy. My frequency, on the other hand, is going to be a little bit more difficult. I've got another trick for that. So we've got the wavelength, that was nice and easy. All I've got to do now is measure the frequency. I said I had a trick, and here it is. No, I'm not going to phone anybody. I am simply going to use the microphone and a little app on my phone to measure the frequency. Now you can see here, it has lots and lots of peaks. This is all the different frequencies being produced right now. Okay? If I make a high-pitched sound, you can see it picks up different peaks. If I make a low-pitched sound, I get, again, very different peaks. So what I'm going to do is nice and simple. I'm just going to hit the rod and measure the peaks on my phone. So let's have a go. Now this is a little difficult because you've got to time it, but let's give it a go. So after a number of attempts, the one number that kept coming up was 3,656 hertz. So this is what my frequency is going to be.
Okay, so let's use this as a little checkpoint then. So just try and remember what the equation is for wavelength and frequency, and then describe how we measure the wavelength and frequency of waves in a metal rod. As per usual, the answers will be on the next slide. If you're watching this on YouTube, now is when you want to pause. Okay, have a go. Okay, so of course the equation for wave speed is frequency times wavelength. Very important that we remember this. And our method, which could easily be in an exam, could easily be, a 4 marker or possibly even a 6 marker if, they choose to, is to measure wavelength. We take the length of the rod and we multiply it by 2. Of course, don't forget, if it's in centimeters, we've got to convert to meters. And to measure frequency, it's very simple. We use a microphone and an app. Okay. Right then, so we have our equation that wave speed is frequency times wavelength, and we have our values that we collected. So now we can start to calculate the wave speed. So the wavelength was 1.22. The frequency was 3,656 hertz. Okay, all we then need to do is sub those in. So of course the wavelength will go there and the frequency will go there, which takes us now to this line. Of course, as I'm sure you are aware, you are always out of calculator, so you want to use one, and we get the answer of 4,460.32 meters per second. Obviously, in an exam, they might choose how many decimal places or how many significant figures to use. Generally speaking, 2 decimal places is always a pretty sound guess to go with if they haven't specified. Now, the nice way here of checking whether this has gone correct is to actually look at what your speed is. We know what the speeds of waves are in different states. So in a gas, so we're talking like air, the speed of sound is somewhere around 330 meters per second. Okay, in a liquid, all right, the particles are closer together, they'll find it easier to transmit the sound. All right, we're looking at around 1,500. In a solid, everything is very tightly packed, neat rows, right? Makes it very, very easy for the sound waves to pass, so it is the quickest. And roughly speaking, we should be looking around 5,000. If you've got an answer when you do this sort of calculation and you're in the thousands, you've probably done this right. If you're in the hundreds, you've done this wrong. If you're in the tens of thousands, you've probably done this wrong. So there is that sort of sweet spot that you should be looking for. And it's a nice way of testing if you've done this correctly, because you might find that you are, 100 out. In which case, you might want to go and check your units, because chances are you might have forgotten to convert centimeters to meters or something to that extent. So remember, in solids, we are aiming for around 5,000-ish.
So let's think about errors now, and we'll start with systematic errors. So in terms of systematic errors, again, we're thinking about sort of measurements, and we're thinking about the equipment we're using or the methods. In terms of the ruler, is our first piece of equipment to think about. Actually, I'm pretty happy to say that the systematic errors are pretty much 0, because the rod is about 60 centimeters long, and this measures millimeters. So actually, the resolution of this is pretty good for what we're trying to measure. And actually, being able to measure an extra nanometer or 2 isn't going to make much difference in the grand scheme of things when we try and calculate this. So actually, ruler's pretty good. In terms of the app I use, well, really, we're talking about my microphone. How sensitive is my microphone? Now, granted, I don't know if there are particular frequencies that my microphone isn't very good at picking out. Now, I would imagine it's fairly good at picking up those ranges, because I was pretty good at hearing it, so therefore I'd imagine this is pretty good at picking it up too. But in terms of errors, really the vast majority, again, come from me. So we're talking about random errors, human errors. Okay? Because as you've seen, I was desperately trying to pause this at the right moments to get the right frequency to pick up the right actual measurement. Okay? But again, I'm there for ages trying to pause it and making it very, very difficult. Granted, I can do lots and lots and lots of measurements to make sure I get there, but again, I could be off. So the vast majority of the errors, again, in this practical, are human errors, random errors.
Right then, now for another checkpoint. So 2 questions just to summarise what we have built on with this core practical. So the first one is just to make sure you are comfortable using the equation, and the second one, describing the systematic and random errors that we faced in this experiment. If you're watching this on YouTube, pause the video now. The answers are on the next slide. Okay, so here are our answers. For the first one, standard equation question, 3 marks would normally be available for this. 1 for stating the equation, 1 for correctly substituting the values into the right places, and of course your final mark for the answer. If you got the answer correct, of course, you would get all of the marks. In terms of errors then, our systematic errors, so we're talking about errors in our methods or our equipment, are actually very minimal. We're using a ruler which has millimeters on it to measure the metal rod, okay, which actually is perfectly reasonable. You could mention that the ruler is maybe difficult to use if it's wobbling, because obviously the metal bar can move, but obviously you could just take it off so you get rid of that issue. Of course, though, as per usual, the vast majority of our errors are caused by human error, which is a form of random error. So we have my eyesight on the ruler to measure the length of it, and of course the issues with timing the hitting of the rod with pausing of the app to actually measure the frequency. So as per usual, human error is the vast majority of our errors. Okay, so that sums up today's lesson. The task that you need to do now is you need to make a revision card to summarize this core practical. As per usual, it is up to you how you want to do this. This is your revision card based on how you think and your understanding. So you need to decide how you want to lay it out. Of course, those that are in my class, as we mentioned before, you are fairly confident with the T method and it seems to work quite well for us, so by all means use that. After you've done that, you need to go on and complete the core practical exam style questions. They are attached to Show My Homework as a PDF. Your best bet is to write the answers to them in your book. Obviously, if you wanted to print them out, you could, but it's a photocopy of the actual page, so it doesn't look particularly clear. So printing it will use a lot of ink. So you are far, far better off just writing the answers into your book. Once you have done that, submit all of this, so your revision card, your questions, to your teacher. And if you're in one of my classes, this will be followed by a live session so we can have a look through these core practicals and make sure we are confident before we move on. Well done today, Year 10. I'll see you all soon.